Hi, my name is Ellie Glenn, and I'm a senior bioengineering student. And for my senior design project, I developed an improved method for the assessment of muscle strength levels for rehabilitation monitoring. Special thanks to my advisors, Dr. Rossi and Dr. Asuri, and my partners, Emma Reeves and Nick Schmager. Muscle strength testing is used by athletic trainers to assess athletes' strength for injury prevention and rehabilitation. Testing results provide baseline strength levels at the beginning of a playing season, then allow for personalized rehab and monitoring of recovery in case of injury. In many cases, an athlete is only allowed to return to play when they can test within a normal range of their baseline strength levels. Currently, the most common devices used to test muscle strength are the handheld dynamometer and the isokinetic machine. These two options have a large gap in both price and performance. The handheld dynamometer is much cheaper, but lacks accuracy compared to the isokinetic machine, which is considered the gold standard for muscle strength testing. The testing protocol for the handheld dynamometer is user-friendly, quick, and convenient. These factors are important when dealing with large groups of athletes, so trainers often opt for the handheld dynamometer even when they have access to the isokinetic machine. Our goal was to find a solution that would address the gap between these two devices by improving the functionality of the handheld dynamometer while maintaining its affordability. After conducting research and interviews, we determined that for our solution to add value, it must be easy and safe to use, allow for quicker testing, and provide accurate and precise measurements. To target these objectives, we proposed a combination of a conventional gym machine found in your average gym and a standard handheld dynamometer. By combining both, we took away the handheld feature of the dynamometer. This exercise machine ensures controlled movement and eliminates the dependence of the test on an athletics trainer's ability to manually resist the force exerted by the athlete. We validated our solution with carefully designed experiments that assessed both accuracy and precision. We used surface electromyography to look at the activation levels of the individual muscles that contribute to force output and determine if a force measurement is an accurate representation of strength. SEMG is a non-invasive, simple method for recording the electrical activity of the motor unit. Muscle activity levels are measured with SEMG sensors placed on large superficial muscles. We chose to focus on testing quadriceps strength because of its significance to many different sports, as well as the accessibility of the three large superficial muscles of the quad shown on the diagram on the left, the rectus femoris, vastus lateralis, and vastus medialis. For our experiments, we placed SEMG electrodes on each of these muscles with ground electrodes on the patella bone. To measure and analyze the EMG data, we used the BioPack hardware platform provided by the bioengineering labs at Santa Clara. The bioengineering system not only records and displays EMG data in real time, but it also performs useful automated signal analysis. To compare relative activation levels during exercises, we looked at the mean integrated EMG value obtained from each muscle. After conducting control experiments to confirm the specificity and sensitivity of our EMG system, we moved into evaluating each method for muscle strength testing. We used the EMG system to monitor muscle activation levels during isokinetic testing, manual handheld dynamometer testing, and finally, with our method for muscle strength testing, which combines the dynamometer and quad extension machine. By comparing muscle activation levels and force output values across these methods, we were able to assess how our solution measured against existing technology. Here's a comparison of one subject's muscle activation levels with each testing method. As you can see, there is a close resemblance in the relative activation of each quad muscle between our solution and the gold standard isokinetic test. With the manual handheld dynamometer test, the muscles are activated in a different way and to a much lesser extent, indicating that this test is not an accurate representation of muscle strength. Notably, the handheld dynamometer machine combination gave greater average force outputs with lower relative standard deviation, which demonstrates the increased accuracy and precision of our solution compared to the manual handheld dynamometer test. In the future, we intend to integrate our improved protocol for a variety of exercises and target different muscle groups. The video on the left shows the manual test method for hamstring muscle strength. In the video on the right, you can see how the control and ease of the test increase by incorporating an exercise machine. We also want to build a device that can be easily attached to a common exercise machine found in the gym, allowing for a quicker setup. We would use force sensing technology similar to that found in the handheld dynamometer, but this prototype would function independently from the handheld dynamometer and could be easily applied for numerous exercises.